Alright, so we're looking at the scalar product, i.e. the dot product. And we have seen this in 2 dimensions. Okay? So this is our 3rd day. Come on. It's not letting me edit. Okay, this is day 3. You'll find it if you look in the notes, not right now, but if you look in the notes, you'll see it as PCH Unit 8 day 3 scalar product of two vectors. Okay. Now, you guys already know the dot product is found by taking the horizontal components and multiplying them together, and taking the vertical components and multiplying them together, and then you add those 2 values together. The scalar product, or the dot product, is a number. Okay? As I graded the test from last unit when you were doing 2 dimensions, there were a lot of people who were doing the multiplication, but then making it like a new vector or something. A scalar product, and that's why that title for this is maybe a little bit more useful than dot product. The scalar product gives us a scalar at the end. Okay? So just as a refresher here, if I'm doing u dot v, and u is the vector 3, 4, and v is the vector 6, 2. What's my dot product?
24.
Okay, 24. It would be 3 times 6 plus 4 times 2. 18. 18 plus 8 is 26. Okay, you say 24?
Yeah.
26. Okay, so there's our dot product. Not a super difficult concept here, but it's a formula you got to know. Now, in 3 dimensions, what do you think we do? What do you mean by the same thing? Very good. Okay, good, Hunter. AD plus BE plus CF. That's all there is to it, okay? So it is the same thing. You're going to multiply the corresponding components and then add all 3 of those values together. And again, you'll get a scalar for your answer, okay? You'll get a scalar for your answer. So we would have, for u dot v here, 5 times 4 plus 7 times 6 plus 11 times 5. Okay? So 20 plus 42 plus 55, that's 97 plus 20, so that'd be 117. Okay, so that would be our dot product. Alright? Pretty easy, right? Now, what did we use the dot product for? You put it over the magnitudes, and that equaled?
Cosine of the distance between the angle between the 2 vectors.
Okay, cosine of the angle between the 2 vectors. Okay? That equaled cosine of the angle between the 2 vectors. So, that still applies if we're dealing with 3-dimensional vectors. The challenge is, okay, the challenge is this. Well, we can easily draw 2 vectors on the coordinate plane and get the angle between them, and see it really easily. when we're dealing in 3 dimensions, it's a little bit harder. But we can still do it because, if you think about it, if I have 2 vectors in 3 dimensions, I could put those vectors so they're starting from the same point, right? And that would be what we'd have to do in order to get an angle between them. So let's say that I made them both start at vector A, and I made this one vector AB and this one vector AC. Okay? In geometry, we know that any 3 points define a plane. Okay? So, while we've graphed things in 3D, it's kind of hard to see the vectors and know exactly what's going on. And also, the plane that we're dealing with, it may not be the plane that has the x and y axis, or the x and z axis, or the y and z axis. It may be some other plane defined by whatever A is, whatever B is, and then whatever C is. Okay? So we've got this angle, this vector here and this vector here. We're getting the angle between them. But the plane could be angled who knows how in that 3-dimensional space. Okay? So just understand that. It's the angle between them on whatever plane is defined by the 2 vectors. But we can do the same thing here. It's the dot product over the product of the magnitude. So if we went back to the one that we had just done, okay, we have u dot v. I'm going to just copy this over for ease. All right. So there's my dot product, 117. Get rid of these. And who knows what these would look like. We'll just call this U and call this V without like plotting 2 points or whatever. You can basically make them, draw them however you want, because we don't know where they're actually started. But we do know the dot product is 117. So then we would get the magnitude. What's the magnitude of U here if it's 5, 7, 11? Good, square root of 195. You do 25 plus 49 plus 121. 49 and 121 would be 170 plus 25 would be 195. Okay? And then vector v, the magnitude would equal what? If it's 4, 6, 5. 16 plus 36 plus 25. What?
77.
77, okay? Square root of 77. So, it's good, you guys have your calculators out. Let's go ahead and plug this into our formula. The cosine of the angle between these 2 vectors is the dot product, 117, over the product of the magnitudes, root 195 times root 77. Now before you get it, hang on. What do I know about theta? What?
Between 0 and 180.
It's going to be between 0 and 180. More specifically, I can actually narrow it down even more.
Between 90 and 180.
Is it acute or obtuse? Between 0 and 90 or between 90 and 180? How many of you think it would be acute? Raise your hands. How many of you think it would be obtuse? Alright, let's try it again so the other 18 of you can actually vote. Think here. Think.
Oh.
Bring that back up. How many of you think it would be acute? How many of you think it would be obtuse? Alright? How do we know? Come on, we should know this. This was last unit. How do we know? Just by looking at the dot product. The dot product is
117.
positive, which means that, and magnitudes are always positive, so that means our cosine is positive. Where is cosine positive?
First quadrant.
First quadrant and fourth, but we know it's not a fourth quadrant angle, so we know that it's acute. Come on, think. Alright, think. You guys can do this. Alright, so what acute angle is theta? Now that we know that. What?
I don't know, just take a guess.
Well, come on, you have a calculator, let's go. What?
17.29.
17.29? Is that what the others of you got? You have a calculator? Come on. Try it. Okay? Listen, guys, one thing I'm tired of seeing on tests is people messing up on their calculator. And that's because we don't practice enough when we're doing problems in class, okay? You should have your calculator out every time we're doing a problem in class. And knowing how to use your calculator should be like this by the time you get to the test, alright? You shouldn't have to think about where stuff is on your calculator. Learn how to use your tools, okay? So, 17.29 degrees would be the angle between these two vectors, okay? Alright, any questions here? Okay. Now, let's look at a couple of, let's take this one more step, and then I do want to look at a couple of properties related to dot products. We'll get to those in a sec here. Finding the vector, or the angle between two vectors when they're being added together. Maybe a little hard to see the arrowheads here, but U is going like this, and V is going like this. How would I find the angle between those two vectors? Or I should say, the angle in that vector addition problem.
I know a really long way you could maybe do it.
You know a really long way you could do it?
If you knew, like, yeah. But that's probably not right.
Well, it might be right, but there actually is a very short way we can do it.
Yeah.
Find theta using think about it. If we wanted the angle between vectors, it had to look like this, right?
Yeah.
So, what's the only problem with this picture?
There's no numbers.
Huh?
You don't have like the points.
Okay, well we could look at this point here. We don't need to know what point exactly that is, but the only problem is U's facing the wrong direction, right? So, how do we make it face the right direction?
Negative U.
Yeah, make it negative. So if we use negative U and V, we could figure out that angle theta. Here's negative U facing the other direction. So now if we use those two, get the dot product and the magnitudes and so on, and use our formula, we can get the angle between those. What would happen, what would we actually get if we used positive U with V? What angle would we actually get?
Oh, we get like the other one.
Outside.
We get like that. Yeah.
The other one.
You'd get what other one? You're right, there's another one.
It's like external.
Okay, if you think of it like an external angle in geometry, if you kept this going, you'd get this angle right here if you used positive u. Alright? So, what do we call that?
Oh, supplement.
The supplement, yeah, the supplementary angles. If we accidentally used positive u, we would get the supplement to the angle we were actually looking for. Okay? So. Okay, let me just remind of some properties here. I'm not going to go through a bunch of examples because we saw these properties when we were dealing with two-dimensional vectors. Just want to remind you, the dot product is commutative, so order does not matter. U dot v is the same as v dot u. A dot product equals of something with itself is the magnitude squared. Okay? By the way, you would never write vector u squared. That is not defined as anything. You might put the magnitude of u squared. Okay? We also had this thing that was kind of similar to the associative property, where if you have a dot product multiplied by a constant, you could multiply either of the vectors by the constant first and then do the dot product. And then we had number 4 was the distributive property for dot product and vector addition. Okay? All right. So, what I want to do the rest of our time here, I'm going to give you guys time to work on some, and there's some good applications here, and just practice using vectors, okay? I'll upload the PDF of this so you can have the problems since they're not in your textbook. But there's a lot of different applications here that are kind of, it's not just straightforward using the formulas. Anybody can plug numbers into a formula. We want to take it to the next level and really work on applying these. So like down here, find t to make them perpendicular, i.e. what's another, and they introduce this term mutually perpendicular. In other words, everything's perpendicular to everything else, which you can do in three-dimensional space. You can have a right angle here and a right angle here and then a right angle out here, you know. And then here you have some parallelogram application. All right, another with a tetrahedron. So there's some interesting applications here that you can work through in the last 40 minutes of class, okay? I'm giving you a lot of time to work through these because I want you to really just take your time, focus, and really work your way through these, okay? All right, let's go ahead and do that then.